Hey everyone, so today I want to cover this problem where we have a cylinder filled with water and we're essentially going to poke a hole right at some point within the cylinder and we're going to see what happens. And specifically what's going to happen is that when we poke a hole, water is going to start coming out and it'll go at a certain distance x, right? And so you can think that, okay, depending on where we poke the hole, the water is going to go like different sort of lengths, right? And the reason for this is because, well, we can think about it in terms of a couple ways. If it's really low, for example, then it won't have that much time in the air to go very far. But at the same time, we know that at the very bottom, the pressure is the highest because it has so much water on top of it. So the speed is going to be like pretty big. And so the water coming in from the bottom will have a big speed, but a small height to travel. If we poke it like at the top, for example, we'll have a big height to travel, but a low speed because there's not that much water on top, so there's not that much pressure. It's going to be a low velocity. And so we might guess that maybe in the middle might be the sweet spot, but we can't really know until we do the math. And so that's what we're going to do. We're going to do the math. And so to do this, we're going to use Bernoulli's equation. And we're going to essentially try to figure out an expression for the distance traveled, which I'll call x, and we'll try to see how we can maximize it in terms of this variable h. So just to introduce some parameters, I'm going to call the big height of the cylinder h, or big H. And I'm going to call the distance from the top to the hole that we're going to poke little h. So this is going to be the variable that we're going to change. So you can imagine that we might put it down here or down here. Okay, so now that we know the mechanics of this problem, let's just introduce one more length. I'll call this length over here just big H minus little h. So that's just using our definitions. Great. So now we're going to have to do a couple things. First, let's pick 2 points for reference. And this is because when we use Bernoulli's equation, this is going to relate the pressures in 2 different locations. And there's many places which you could pick to work this problem out. It's very similar to like when you're solving like a gravitational potential energy question, for example. You can set the 0 to be anywhere you like, and the physics will be the same. But some spots are more convenient than others. And so I will argue that one of the most natural spots to put it is at the hole itself. So let's call it point 2. So that's the point where, the water is going to be coming out of. And the other point we can put in many places. For example, we could put it like over here, for example. But I think the most natural place to put it, or at least the most convenient mathematically, again, physicists are lazy, so we want to take shortcuts, I think it's at the very top, P1 over here. And the reason is because now if I ask, let's apply Bernoulli's equation, I can say, okay, the pressure at point 1 is going to be atmospheric pressure because it's at the very top of the cylinder. It's contact with air, right? And that's actually also going to be the case for the point here. It's also touching air, so it's also going to have atmospheric pressure, which means that both P1 and P2 are going to be equal to each other. And the nice thing about that is that if they're equal to each other, that means that we can just subtract them nicely from our equation, and it just disappears. So just by virtue of picking points that work nicely, we can just cancel those out perfectly. And so great, we've just removed 2 terms. Let's see what else we can get rid of. And the next thing that I'm thinking of is these sort of gravitational terms. And so for this, we're going to have to set a gravitational potential energy 0, which again is similar to when we've done it before with like a ball falling from a certain height to the floor. The most natural, I would say, point to pick would be at point 2 itself. So we can define that to be our 0. And the reason why I choose this point is because this value of h, what it essentially measures is the distance from your arbitrary 0 point. And in this case, point 2 is just a distance h2 equals 0 from our point because it's on the point itself, which means that since h2 is 0, this will be 0, which means this whole term is 0. So now we've gotten rid of 3 whole terms, which is awesome. Note that this is not the case for our term here for point 1, because it's going to be a certain height above from P2. In fact, it's going to be definitionally h above. So we can remove the sort of sub 1 here, and we can just write it as h. So, okay, we have these 3 terms. Can we simplify it even more? And the answer is yes, but this one's a little bit more conceptual. And so the way to do this approximation is to think about the continuity equation, which says A1 V1 equals A2 V2. And what this is saying is, because we're assuming that water is conserved here and it's incompressible, because that's the case, the flow rate from the top of this cylinder and this hole, they have to match each other. Like the amount of water that's leaving has to be the same. In other words, the cross-sectional area times the velocity of the fluid have to be the same for both holes. And so the way to think about it is, when I open this hole here, water is going to start coming out really, really fast. And it's really fast because the hole is really, really small. So area is very small, or I guess it would be here because it's 0.2. Area is really small. That must mean the velocity has to go up to compensate. Meanwhile, up here, the cylinder is going to start draining, and since it has such a big area, it's so big in terms of its cross-section, that must mean that the velocity is slow. And the thing to think about here is compare the size of this hole, which is really, really small, to this sort of top of the beaker. It's really, really big. In other words, if this velocity is really, really big because of the smallness of the hole, then this velocity here is going to be super, super, super small compared to the other velocity. And if you're not convinced enough, let's say, for example, the V1 turns out to be like 0.1. In our term here, in Bernoulli's equation, we have V1 squared. And it turns out that when we have a small number and we square it, it becomes even smaller, like when it's less than 1. And so, for example, V1 squared would be 0.01, and this would be like meters squared over a second squared. But the important thing is, numerically, this would be a really, really small number, even smaller. And what this means is we can say, all right, if it's going to be that small, let's just say that it's 0. Let's just say that it drops off. And this is valid in this context. And so what that means is we can say, all right, awesome, I'm going to get rid of this, or no, I'm getting rid of this term over here, because this is the velocity that's really slow. And so what are we left with in the end? Well, we're left with rho, which is the density of the fluid, G, all these things, is equal to a half rho V2 squared. Perfect. And notice how we actually don't care about the density of the fluid, because it just, it cancels out. And so we know everything else. G is just a constant, h is a parameter that we've defined. So now let's just solve for the velocity. So I'll multiply both sides by a half, by 2, and I'll get 2h. I'll take the square root, and this will. So we've just figured out the velocity of the water coming out of the beaker. That is awesome, because now we're done with fluid dynamics. Now we're just going back to kinematics. And again, physics builds upon itself, so it's important to keep paying attention. So, let's just model the water going like this. We now know its exit velocity. Specifically, we know its, x velocity. And let's just call this distance x. So now my question is, given that we know this exit velocity, what is the value of h that will lead to the furthest possible distance? So at what point in this height here will the hole sort of give the most distance once the water is released? And so to figure this out, we're going to have to use some kinematics. And so what I'll do is I'll consider the y, the change in y. And so in other words, what I'll say is my change in height is going to be equal to a half gt squared. And I use this equation because here what's going to happen is that our acceleration is due to gravity. And it turns out that we're assuming there's no air resistance or friction. And so we're going to assume that the x velocity, what we figured out before, that's going to stay the same throughout the whole trajectory. And so the thing that's going to limit this water's sort of like trajectory is going to be the fact that it's eventually going to hit the floor. And so now let's figure out how much time that would take. And so I'm going to replace delta y with the full height, which is big H, because that's the full height, or well, actually, never mind. that is not correct, because the height that it's going to drop is going to be big H minus little h. So I'll say this is the case here. So hopefully this makes sense. This is the height that the water is actually going to drop. And we can see that as we increase h, this height is going to decrease in size, because it'll become smaller and smaller. Great. So now let's just solve for t. So we're going to multiply the right-hand side by 2 and divide by g. So we'll have 2g parentheses h minus h. The h's are confusing. And finally, we'll take the square root. And this is going to be the time that it's going to be on the air. So now we're almost done. So now what we have to say is, all right, x, the distance that it travels, is going to be equal to its x velocity, vx, which in this case we've called v2. So I'll go back to that notation, v2, and the time that it travels. We've just figured out the time, we know the velocity, so how about we move this over here and let's just multiply. So we're going to get our velocity is the square root of 2gh, and we'll multiply that by the time, which is here. So this is going to be 2g, or 2 over g, h minus h. Perfect. And so now we can simplify a few things. So for example, this g and this g are going to cancel because they're both under the square root. This 2 and that 2, they're going to become 2 squared, and since it's inside the square root, we can pull it out. So I'm just going to rearrange this real quick, but you should be able to see that we're going to get 2 times the square root of h, big H minus 8. So this whole thing over here. All right, so what we figured out is, if you were to tell me, all right, I'm going to poke the hole at this distance h, I can tell you exactly, assuming no, friction from air and air resistance and all that stuff, assuming none of that, I can tell you exactly where the water is going to land. So this is the physics so far. At this point, if we wanted to find the ideal, the optimal sort of h spot, there's a couple things we could do. So one of my recommendations would be to plot this in a graph and to see what happens, to experiment and see where the peak of the graph is. It's going to end up being a parabola. But I think this is a problem that is really meant for, an optimization problem in calculus. And so what I'm going to do is I'm going to find essentially the maximum value of x as a function of little h. And so here's how I'm going to do it. So I'm going to organize my workspace. That's very important. I'm going to put this over here. And now what I'm going to say is, all right, this function is going to be at a maximum when the derivative of the function, so dx, dh, because h is our variable here, when the derivative is 0. So you can think of, if this is a parabola like this, its peak is over here, and its rate of change of that peak is going to be 0, because it's going to be a horizontal line. And so that's what we're going to solve for. So that means that we're going to have to differentiate this function. So what that means is dx, dh. So the way that I'm going to do this is I'm going to rewrite this real quick in a clearer way. So I think I'll start by doing this. So I'll write this as 2 square root, and I'll just expand this thing inside. So again, you could probably use the product rule, but I think this might be a little bit easier. We get this function over here. And now let's differentiate it. Actually, I'll just write it in a slightly clearer way. I'll write this in terms of, to the power of 1/2, which is equivalent to square root. So now I'll differentiate this function, and I'll use the chain rule. So I get 2 on the outside. Now I'm going to differentiate this, so I'm going to get 1/2 over here. We're going to get the function, so h, big H minus little h squared. And now we're going to subtract 1 from the power. So the math isn't super critical, but I still want to show it because I think it's cool. So we're going to get this, and now multiplied by the derivative of the inside. So in this case, we're differentiating with respect to little h. So we're going to get big H here minus 2 little h. And that's our answer. Or, well, that's our answer so far. So what we're going to say is, all right, this is equal to 0. That's our condition for finding a maximum. And so this simplifies things nicely because, first of all, this 2 and 1/2, they're going to cancel out. Now we can divide by this whole nasty term, just both sides, and 0 divided by that is 0. So this whole thing is going to go away. And so we're left with h minus 2h equals 0, which means that h equals 2 little h, Or if we solve for little h, we're going to get that little h is equal to big H over 2. And this is our final answer. So what does this mean? Well, it means that if I want to maximize the distance traveled in the x direction from the water, I have to poke the hole exactly at half of the height of the cylinder. And so this is the exact optimal position where it balances out the effects from pressure and the effects from height to grant us the largest x direction, or the largest x displacement. And so the calculus isn't super important, although I think it's neat. And I highly encourage you to like go on Desmos and to plot this function and to sort of experiment with it yourself. But I think it's just cool to show. So yeah, I hope this was helpful, and let me know if there's any questions.